Assalamualaikum warahmatullahi wabarakatuh. Today, my team and I gonna present about article that we choose, which is analysis of power flow and short circuit fault. So, our team have been conceived of 5 team member, which is myself, Muhammad bin Muklis bin Zulkifli. We have Muhammad Ahmad Zainal, Muhammad Azhar bin Aidil, Muhammad Iqbal Haziq bin Noazli, and the last one is Muhammad Daniel Fitri bin Muhammad Shahrul Nizam.
Hello, Assalamualaikum. My name is Daniel Fitri bin Muhammad Shahrul Nizam. I will be presenting about the power system network topology. In this study, the power system is modeled as a balanced three-phase interconnected network. The system consists of generators, transformer, and transmission line that are connected through multiple buses. Each bus represents an electrical node where power is generated, transmitted, or transformed. The overall network topology defines how electrical power flow throughout the system and how disturbance, such as faults, affect other parts of the network. Understanding this topology is essential because it forms the foundation for analyzing short circuit behavior and system protection. Next, we go to the network modeling assumption. Several assumptions are made to simplify the analysis. First, the system is assumed to operate under balanced condition before a fault occurs. This allows the use of symmetrical component theory. Second, electrical loads are neglected during short circuit analysis as their impact on fault current is relatively small compared to network impedance. All system parameters are expressed using the per unit system, which ensures consistency and simplifies calculation. When fault occurs, it is assumed to happen at a specific bus. The entire power system is analyzed from the perspective of that faulted bus. Alright, we go to the next slide, which is sequence network presentation. To analyze unbalanced fault condition, the power system network is decomposed into 3 sequence networks using symmetrical components. The positive sequence network represents normal balance operation and contains the system voltage source. The negative sequence network represents the effect of unbalance caused by fault, while the zero sequence network represents ground and neutral current path. Each sequence network is modeled using a bus impedance matrix, which reflects the physical connection and electrical characteristic of the system components. Next, we go to the topology behavior during fault condition. During symmetrical fault, the system remains balanced and only the positive sequence network is involved. In contrast, during unsymmetrical faults, the positive, negative, and zero sequence network become interconnected at fault location. The way these sequence networks are connected depends on the fault type, fault location, and grounding configuration. As a result, the network topology directly influences the magnitude of fault currents and the fault voltage distribution across the system. Therefore, accurate modeling of power system network topology is critical for effective protection system design and reliability of power system operation. That's all for me. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azhar bin Aidil, and right now I want to continue our presentation in our assignment. So my part is power flow circuit. So this is our circuit. This circuit we create in software Power World, and we just refer to our article that we find in Google. So this is the circuit, and after this I want to present what we use in our circuit how much bus, how much the generator, how much the transmission line, how much the transformer that we use. So let's go to the next slide. Okay, so right now I want to present all of you about list of equipment in the power system diagram. So in this slide, I want to present about what we use in our power flow circuit. So before this slide, I just show all of you the circuit that we create in power world. So right now I want to present what we use in the software. So firstly, we have a generator in the circuit. In our circuit, we have used two generator, which is generator 1 located at bus 1 function as the slack swing generator. So the generator 2 located at bus 6 operate as a PV generator. So we have transformer in our circuit. We have used three transformer, which is transformer 1 connected between generator 1, bus 1 and bus 2, transformer 2 connected between bus 5 and generator 2, bus 6. So in transformer 3 connected between bus 11 and bus 10. Okay, supplying the asynchronous motor. So we not use motor because we don't have any equipment of motor, so we just use load because our motor is load in this circuit. So we have used a transmission line. We have 13 transmission line, which is bus 2. In bus 3, we have a transmission line. Bus 2 in bus 4, bus 3 to bus 5 have a transmission line. Bus 3 to bus 6, bus 3 to bus 8, bus 5 to bus 9, bus 7 to bus 8, bus 8 to bus 9, until bus 12 to 13. We have a transmission line. So after that, we have buses. We have a total of 13 buses labeled bus 1 to bus 13. So each bus represent a node for power injection and withdrawal or interconnection. So we have loads. We have load at bus 4, and then we have load at bus 9, and then we have load at bus 13, and then we have asynchronous motor, which is load model as load. So the load of motor is located at bus 10, and the approx is 42 megawatt with a 0.45. Every load have a different value. So we have synchronous motor, which is supplied through transformer 3, represent in power as a constant PQ load. So we have a circuit breaker. The circuit breaker is a switch. So circuit breaker located at generator terminal. A transformer connection, line connection at bus used for protection, isolation and fault studies. So, and lastly, we have a measurement and direction indicator, which is about power flow arrow showing direction of real and reactive power, MW and MVAR annotation at generator at load. Okay, so the measurement and direction indicator, this you will see when I run the software, and you can see the power flow arrow showing in the transmission line in the power flow circuit. So that's all for me. Thank you very much.
So next we will go for the next slide, which is the type of short circuit fault. So we have four of short circuit fault, which is we have single line to ground fault, we have double line to ground fault, line to line fault, and then the last one is three phase fault. So we will go one by one, which is single line to ground fault. This fault occurs when one phase conductor accidentally touches the ground or earth. It is the most common type of fault in the power system and usually happens due to insulation failure or lightning. The fault current flow from the phase to the ground. The second one is double line to ground fault, which is we known as LLG. This fault happens when two phase conductors come into contact with each other. Ground is not involved in this type of fault. It commonly occurs due to strong wind, conductor swing, broken insulator, and it causes unbalanced current in the system. The third one is line-to-line fault, which is we known as double L, LL. In this fault, two phase conductors touch each other and also come into contact with the ground. It is more severe than a line-to-line fault because ground is involved, insulating a higher fault current and greater system disturbance. And the last one is three-phase fault, which is we known as triple L. This is the most severe type of short circuit fault where all three-phase conductors are shortened together. Although it is occur less frequently, it produces a higher fault current and is often used as the worst case condition in power system design and protection studies. Okay, this slide is talk about the setup to check a fault in the power world. So before we check a fault, we need to make a fault. So go to the previous circuit simulation, choose one bus that you want to make a short circuit fault. And then for this assignment, we choose bus 4. So make sure the simulation in run mode, just right click at the bus and then choose fault. So after you choose fault, this figure will be appear. So what you need to do, just choose the fault location, which is a bus fault, and then the type of fault. Like I said previously, we have a several fault. So for this assignment, we choose line-to-line fault and then just press calculate, and then the system will calculate for you the value after the fault. So the value at the bottom of the figure. Okay, if we can see on the slide, this is the value of every bus after the fault. So if you can see, we have 13 bus, and then the system will calculate for you for the phase for volt A, volt B, and volt C. Also the phase angle for A, B, and C. So if we can see, this is the value after we make a line-to-line fault for the bus 4.
So right now, I will present about the legal and regulatory standards. So we know that there are so many legal and standard in power system, but this is the main standard that have been listed. So the first standard is Electricity Supply Act 1990, which is the Act 447. It is about the Malaysian law that requires all electrical system to be designed and operate safely to protect people and property. And for the second one is the Electricity Regulation 1994, which is it is about provide technical rules on protection, cable sizing, earthing, and equipment rating based on short circuit study result. And the third one is about Suruhanjaya Tenaga approval. It is about all electrical project must submit engineering studies before approval is granted. So the fourth one is TNB distribution code. It is about to set voltage limit, fault level limits, and protection coordination for distribution network. The fifth one is about TNB grid code. It is about control stability and safety requirements for high voltage grid connection. And the sixth one is IEC 60909. It is about international standard for short circuit current calculation method. And the next one is IEC 60076. It is about standard for transformer design, testing, and fault withstand capability. And the next one is IEC 62271. It is about standard for circuit breakers and switchgear safety and interrupting capacity. And the next one is IEC 60255. It is about standard for protection relay performance and reliability. And the last one is IEC 61439. It is about the standard for switchboard and panel design to withstand heat and fault current. Then I will present about the technical reference. which is there are three reference that we refer, which is the first one is IEEE 14 about the bus test system. It is about a reference power system model used to validate analysis methods and simulation result. So for the second one is IEEE 3000 series, which is it is about technical reference for power system analysis and protection practice. And for the last one is power system textbooks and journals. It is used as supporting technical reference and for result benchmarking.
Assalamualaikum and hi. My name is Muhammad Ammar bin Zainal, and my part I will begin by discussing the societal cultural aspects of power system analysis. And this slide is more focused on public safety, quality of life, and also public trust. So for the societal and cultural aspect, for the first point is public safety. Short circuit analysis is important because helps prevent electrical accidents such as a fire and equipment failures. When a protection system works properly, it ensures the safety of people, public infrastructure. The second point is quality of life and social dependence. Today, almost all daily activities is dependent on electricity, including hospitals and also education and also communication. A reliable power system reduces power interruptions and helps maintain a better standard of living. And the last but not least, the third point is public trust and cultural expectation. In many societies, a stable electricity supply and represent development and technological progress. When the power system is reliable, public confidence in electricity providers is increased, while a frequent outage can lead to desertification. So now we are moving on to a reliability of the power system analysis. The first aspect is accurate fault current calculation. This is very important because it allows engineers to determine the correct level of short circuit current. With accurate values and also protection device such as a circuit breakers can be selected and operated safely. Next is effective protection coordination. Proper coordination ensures the only faulty section of the power system is disconnected during a fault. This helps reduce unnecessary power outage and improve a continuity of supplies. And finally, equipment protection and system stability achieved through a reliable fault analysis. By limiting the excessive stress on generators and transformer, the equipment life can be extended and the overall power system remain and stable. And that's it from us. Thank you very much. And that's it from us. Thank you very much.